and that's how he got hired, and the other dude got hired for career fair.
Yeah, because
Yeah.
All right, how's everything going?
Good.
More
Math test
heaps?
today.
What?
Had a math test today.
Had a
Sounds like
math
three of us
test?
had a math test.
Oh, how was it?
Not
Yeah.
as bad as I was anticipating it.
Is this linear?
Yeah.
Okay. Good stuff.
It sounded like it was going to be a nightmare yesterday.
Yeah.
Always those.
I always loved courses where you had like these horror stories ahead of time, and then it turned out to be like not too bad.
Yeah, like we had this whole spiel about when you have to find a determinant of like anything larger than a 2 by 2, you have to like collapse a column,
Yeah,
or
yeah.
collapse a row, and then you have to add that to whatever.
Mhm.
We never even had that.
Okay.
So, thanks.
That's a good recursive thing too. You can do
Well,
determinants recursively.
You can do that.
Yeah.
One thing that's interesting is taking the recursive function and making it explicit. And
Mm-hmm.
it's like, why don't we just start there?
Yeah, yeah. All right, so let's look at heaps again. So I'm going to draw a heap, and I'm just going to use letters for the nodes instead of putting actual values in, but we'll assume this is a legitimate heap. So the way I'm drawing this is important. I'm filling each row in from left to right, and when I get to the end of that, I go down to a new level. So if I want to add another node, I'm going to start a new level. It's going to be H, I, J, K, L, M, N, O, and so on. And we're going to ignore the values of those nodes for the time being, and just look at the shape of this. And if we wanted to write code to implement a heap in C, for example, we know how to make a binary tree, right? We can have a node, we can have pointers to the left and the right, and so on and so forth. We can do the same thing for a heap, but it turns out we don't have to. There's a cleaner way to implement heaps, and that's using arrays. And this is, to me, the fun part of working with a heap. So we're going to make just a plain old array.
Your video is kind of freaking out a little bit.
Yeah, like stutter steps.
Yeah.
Yeah, I don't know what the deal is. And as usual with arrays and C's, we also need to know how big our array is. So I'll have a variable heap size, which tells us how many things we have in our heap. And here's the trick to using an array for a heap. We don't use element 0. We start with element 1. That's really important. And we store the elements of our heap in order, in the same order that we would add them to a heap. So starting with the root, moving down one level, storing from left to right, and continuing. So conveniently, these will just come out alphabetical. So heap size is 15. And I'm just using heap size to be the number of things in our heap, since we're not using 0. In this case, heap size is actually the index of the last element. So we don't have any of that -1 business that we always see with arrays in C. Okay, so what's the advantage of doing this? Well, if we have a node I, we can make a function to find the parent of that node. And the parent is just the integer value of I divided by 2. So for example, if we want to know element k's parent, k is stored at index 11. 11 divided by 2 is 5. Element 5 is e. E is k's parent. And if we wanted to find J's parent, J is element 10. 10 divided by 2 is 5 is element E. E is also J's parent. So finding the parent of a child is easy. We just take the index of the child and divide by 2, treat it as an integer. And we can go in the other direction. We can find the 2 children of a node, and it's just 2 times I, or 2 times I plus 1. So if we want to find node C's children, C is at index 3, its children should be at index 6 and 7. That's F and G, the 2 children of C. So it's very efficient to move through the heap from child to parent or from parent to either child. And it's just some simple index arithmetic. Okay, why is this nice? Because everything we do with a heap, heapifying, heaping up, upheaping and downheaping, basically require us to just move through the tree, either up or down. And we can do that with the corresponding array just by doing these simple index manipulations. All right, there's no catch. It's really this nice. So if we want to insert, so let's say add a number n to our heap. So when we want to add something to the heap, where does it go initially?
Oh, it just goes on top.
Doesn't go on top. It goes on bottom. It goes at the rightmost position on the bottom row.
Oh,
Or we start a new row if there's no space left. So if we wanted to add a new number, it would initially hang off of here, right? And where is that in this array that corresponds to the heap?
16.
It's 16.
It's index 8.
It is index h multiplied by 2, but it's also just index heap size plus 1. Right? So when we add to a heap, we start off by putting it into the last position on the heap. That's always just the next element in the array. So to add a number n, we can say something like heap, bracket, and we can pre-increment heap size and set that equal to n.
As long as we still have an index.
That's what?
As long as we still have an index.
As long as we have an infinite array here, that makes it convenient. And then what do we do after we add our new node down here? How do we get this back to being a heap?
Up.
Up heap. So I'm going to call an upheap function. I'm going to pass it the index of this node we just added, which is heap size. And this will presumably adjust the array, and we're done. Okay, how do we remove whatever's at the top of the heap? Whether it's a min heap or a max heap, the smallest or the largest. How do we remove something from the heap?
So like its children.
What is it?
The-
Okay, so we want to return the root, right?
So heap at index 1.
So save equals heap at index 1, and eventually we're going to return that. So we're going to get that out of the heap, and what do we replace it with?
The max value between these.
Yeah, the rightmost on the bottom layer, right? So the last entry. So heap bracket 1 equals heap bracket heap size, and we'll post decrement because we've got one fewer things in the heap. So that moves the last node up to here, and then we can call down heap on the root, and when we're done we can return save. So removal is really easy too,
Parent of up heap and down heap.
as long as you have up heap and down heap, so you get a friend to write those for you. So how do we down heap?
You check it, children.
Okay, so down heap. From some index I. So we want to compare this value to the value of the two children. And let's just suppose we're doing a max heap. So compare node I to its two children, and if it's not bigger than both of them, swap with the largest child, and then down heap from that child on down. So we can do this a variety of ways, but compare node I with children. So if heap I is bigger than or equal to heap child 0 of I, and heap I is bigger than or equal to heap of child 1, then return. We're satisfying the heap property, we don't have to do any work. Otherwise, swap with the largest child. So if child 0 is the bigger child, then we want to swap node I with node child 0 I. So swap heap I with heap child 0 of I, and then down heap from child 0 of I. Else do the same thing with child 1 instead of 0. So you could write this a lot more efficiently, but this is written out explicitly. And the swap's just the usual temp equals A equals B equals temp kind of thing. And we've written this recursively, we're calling down heap here. But remember, if you're doing a recursive call as the last thing in your function, you don't need to recurse. You can usually replace that with a loop. Right, we could simply set I equal to child 0 of I and then go back up here and re-execute this code. And we need an edge case. So if no children, then return. Bless you. So our child function will just happily give us a new index, but we want to check and make sure that's not bigger than heap size. If it is, then that child doesn't exist. So if there's no children, we don't have to do anything down heap. Otherwise, compare yourself to both children. If you're not bigger than both of them, swap with the largest child and down heap from there. So that's not bad, and it's an order log n algorithm. And up heap is exactly the same structure. Right? You start with a node, you compare the parent of that node to, you can compare it to both children, you really just need to compare it to the node that you're looking at. And if it's violating the heap property, swap with the appropriate child, and then up heap from the new parent, and just keep going. So this is really fun to code because there's no dynamic memory, there's no pointers, there's no mallocs, there's no size of, there's none of that stuff. It's just a plain old array, right? You can do this in Fortran, and it works great. And that's kind of cool because it's this really powerful structure. It's very efficient. It's got log n characteristics. but it's just a good old array. So that can be pretty cool. Yeah.
When talking about big O notation or whatever,
Mhm.
when you say log n, does it matter what the base is?
We're usually talking about log base 2,
Alright.
but what's the difference between different bases?
It was log base n and not just be 1 there. If it's log base 1.0001.
Yeah, so log 2 of n is log 10 of n divided by log 2 of 10, I believe.
Yeah.
So it's a constant multiple, and constants get absorbed in this big O notation. But for actual degree of complexity, that can make a difference. And we're going to go back to Radix Sort in a second and play with just that idea.
So you want to use a heap as long as you don't search for a specific value, right? That's
If
the
you're not
only thing.
searching for a specific value, then a heap's generally a pretty good way to go.
So is that what most people use then? Like,
I don't know what most people do. I don't understand people.
Like that might be a better alternative to the way we're doing keys.
It might be. Now, one downside to this is this index arithmetic. If you're down at element 1,000,000 and you want to find that node's child, that's going to be 1,000,000 spots down the array. And there's this notion of locality that can be important when you're dealing with large amounts of data. When we pull information out of memory, we usually don't go directly to the main memory, right? The main memory is that stick of memory you buy from Best Buy or Amazon or Newegg, and you stick in your laptop or your computer, right? That's main memory. We don't usually read our memory from there. We're usually reading it from a local cache that's stored in the CPU, an L1 cache or an L2 cache. It's just like the caching idea for dynamic programming, right? It's a local copy. Reading a value from this local cache in the chip is fast. Okay, our CPU is running at 2 or 3 gigahertz. Okay, that's like half a nanosecond per clock tick. We cannot get to main memory and read a value out in half a nanosecond. It takes way, way, way more time than that. So the reason that we can run our CPUs in the gigahertz range is because most of our memory accesses come from this local cache inside the CPU, physically on the same chip. A nanosecond, how far does an electron travel in a nanosecond? Anyone know the rule of thumb? It's about 12 inches per second. Right, so if you look at a motherboard in a PC, and you look at the distance from the CPU to the memory and back, that might be a nanosecond just in electron travel time, which means that your max clock speed is going to be a gigahertz, effectively. So we got to have this local cache to keep things running. And something like this might completely destroy your cache coherence. It might totally destroy your locality of data. Now, when you build a binary search tree and you're using mallocs, each time that you call malloc, you probably get a chunk of memory pretty close to the last chunk that you malloced, right? Because they're coming out of some structure. Not always, because the stuff gets fragmented. But 1,000 calls to malloc, you're probably going to get 1,000 blocks fairly close to each other. And when you create a child for this node, it's probably going to be a value fairly close to that parent. And so you may get better cache performance using dynamic memory than you do with an array. Arrays are notoriously bad for memory performance unless you're going strictly from beginning of array to end of array.
you know, like you're using just structures, would be way more efficient.
Probably, yeah. So there's so many considerations, right? But the overriding one is this is fun to code, so it's a good way to go. All right, other questions or comments on heaps? Let's go back to Radix Sort for a minute. So Radix Sort, remember you have your numbers stored as, say, a series of digits. And we go through and we sort by least significant digit and then increasingly significant positions. And when we're done, everything's sorted magically. And a way to sort by this digit, if we know that these are decimal numbers, so radix 10, we can make 10 passes through our numbers. On the first pass, we grab anything that has a 0 in this position, and we copy it to our output array. And we just keep tacking to the end of our output array, so just increment some output index. And then make another pass and look for anything that ends with a 1. Make another pass looking for 2s and 3s and 4s and 5s and 6s and so on. And after 10 passes, everything that's in your input array will have been copied into your output array. And they'll be copied in the order of this least significant digit. So the order of complexity is basically, a fixed number of passes times however many digits you have, times how much work you have to do in a pass. So you definitely have n pieces of data. There's an n in there. I'm not going to worry about the radix because that's fixed regardless of the data. But the number of digits, d, that's basically your order of complexity.
Since D is an integer.
And d is an integer, and so this is the same thing as order n.
It's just more efficient than more digits per.
It's more efficient, but the digits definitely cost more time, right? But in terms of big O notation, it's still order n. And things like merge sort, which are order n log n, would seem to be less efficient, right? Because it's n log n that's bigger than n. But let's think about radix sort. If we were to apply this to integers stored in binary, okay, so write your integers out as 32 binary bits. And how many 32-bit integers are there? 4 billion. Okay, so suppose we have 4 billion integers. So that's the approximate value of n. That's a lot of integers, right? That's presumably the most that we would try to sort because that's the set of all 32-bit integers, right? Well, if n is 4 billion, what is n log n? So what's the log of 4 billion? I didn't just give it away. 32. So this is 32n. If we're doing a radix sort on 32-bit integers written in binary, how many digits do we have? 32. These are both taking roughly 32n operations. So even though this looks like it's more efficient because it's n versus n log n, that log n is actually really, really small. And this d is potentially really, really big, right? To the point where if we were to do this on 4 billion numbers, we basically get the same number of operations. So the big O notation can be deceptive sometimes. Usually if we see an n, it's going to be better than an n log n. It's going to be certainly better than n squared. But if you wanted to sort 5 numbers, a bubble sort may be more efficient than a merge sort or a quicksort, because those other sorts have a lot more overhead. They may require you to allocate temporary memory, and there may be a lot of startup time and recursive calls if you're doing a merge sort and so on and so forth. And a bubble sort of 5 numbers is pretty simple, right? It's still a handful of operations, 15 operations or something, but that may be lower total time. So these are asymptotic expressions, right? As n gets bigger and bigger. At some point, this will be less efficient than this, but that point may be beyond what we're reasonably interested in doing. So that's something to keep in mind. freaking out? Yeah. That's weird. All right. So let's do a more interesting example with Quicksort, because we did kind of a short example the other day. So let me try to make a better list of numbers. So this will be Quicksort. A random list of integers to sort with a quicksort. Okay, so how does quicksort begin? Choose a pivot. We're going to pick the rightmost. All right, then you need a pair of colored markers. So we're going to go green and red. So we're going to have a pair of indices, right? We're going to start with the first number over here and the last number over here. And when we're looking at green indices, starting from the left, what's our goal?
Find something bigger than
We're looking for something bigger than 20. 10 is smaller than 20, that's okay. We're going to move on to the next number. 5 is smaller than 20, that's okay. We'll move to the next number. 25 is not smaller than 20. That's where we stop. And we switch to the other index. So now we're looking for things that are smaller than 20. 29 is bigger, that's allowed. Come down to 13. 13 is smaller, that's a violation. So we stop. When both arrows have stopped, now we swap what we're pointing to. So we're going to swap these two. And now we're going to have 10, 5, 13, 27, 8, 32, 4, 16. And this becomes our 25, and the 29 stays here. And the 20 is our pivot. All right, and we are sitting right here and right here. Okay, and we go back to the beginning. So we start moving the green arrow. We move it over to here. This is bigger than 20, we stop. We go to the blue arrow, move it here. That's smaller than 20, we stop. We have to do another swap. So swap these two elements. So the 27 becomes an 11, 8, 32, and so on. The 11 becomes a 27. And our pivot. And now we're pointing at an 11 over here and a 27 over here. And we just keep doing this. Now each time that we do this, our arrows are moving towards the middle. Right, we're making progress. And worst case, we're going to end up moving between the two arrows a total of, say, roughly n positions. Right? We might move this one a lot and this one a little. We might move them both equally, but eventually they're going to meet. And at that point, the amount we've moved this and the amount we've moved this is going to be roughly n, where n is the number of items. And at each step, what do we have to do? We have to compare the number that we're pointing to with our pivot. And potentially, we have to swap two numbers. Okay, that's all a fixed amount of work. So this whole process is going to be order n. Okay, but it's gonna be a big N because I'm slow at drawing things. So 8 is smaller than 20, 32 is bigger, stop. 62 is bigger, 45 is bigger, 17 is smaller, stop. Swap these. This is 17. This is 32. All right, 4 is smaller than 20, 16 is smaller than 20, 41 is too big, 32 is bigger, that's fine, you come over here, 41 is bigger, that's fine, but now our arrows have met, so this process stops. And once it stops, we take this number and we exchange it with the pivot. And this gives us our final array. Right there. And we're going to circle this thing that was our pivot. And the circle means this is in the correct spot. And the goal of this whole process was everything to the left of this position is smaller than 20, everything to the right is bigger than 20. All right, so this whole collection of steps, basically order n. And then all you got to do is sort this and sort that. And you do those by calling Quicksort.
Your base case be n equal to 1 return.
Your base case is if n is equal to 1, just return. So yeah, let's not forget that. With only one number, then you're done. So this isn't too bad to code, right? You need a pair of indices. So you could have this stuff stored in an array, right? That'll work perfectly fine because we're not inserting or deleting in the middle of the array. We're simply swapping pairs of elements. And you have an index that starts with index 0 and another that starts with index n minus 2. And you compare element first index to pivot. And keep going until you have to stop, move the second one until you stop, swap those two elements, keep going. And the whole loop stops when your two indices are pointing at the same number.
Oh, so the function would take an integer pointer for your array and two integers.
Mm-hmm.
Read the index.
Yeah. And then when your pointers meet, swap that element with the pivot. And then you have to somehow break your array up, so you pass everything before that new element to Quicksort. You tell it you have this many, and then you pass this stuff to Quicksort. And if it sorts it in the array, right, then you're just done. And so the other thing, we mentioned this the other day, since you're roughly dividing the list in half each time, the number of times you have to do this until you get your base case is log n. So n operations per pass, log n passes, that's the n log n. But the worst case that we also saw is when this array was close to sorted to begin with, your pivot may end up moving over maybe just 1 or 2 positions, and then your subcase is almost as big as your original. And in the extreme, you end up having to do this whole process n times, each one order n. That's your n squared, your degenerative case. So general C question here. That's going to be really annoying to watch. General C question here. Suppose you have an integer array. Okay, we're calling it data, and you have an integer that tells you how many things are in your array. Okay, like data size. So first element is data 0. That's easy. What's the last element? Right, it's data size minus 1, because we index from 0. Now suppose we wanted to split this array roughly in half. So halfway point. And we'll do integer division, so let's just call it 37. I would probably do data size minus 1 over 2. But let's just call this the halfway point. So if I wanted to call Quicksort on the first 37 elements, let's say, right, I could say Quicksort data, comma, 37.
Yeah, my question was going to be, how do you get the second name?
Yes.
That's
So how do we get the second half? First of all, we need to know how many elements it's going to be, and it's not going to necessarily be the same, because we got an odd number of elements, so it's going to be 75 minus 37, so 38.
You ultimately want to pass it. You ultimately want to pass it number, not element 38. Or 38.
Yeah, so one way to do this is like this. Pass it the address of element 37. And to the Quicksort program, which is expecting an integer star, it just sees a pointer to the 38th element in your array. It doesn't know that that's part of a longer array that the caller was working with. It just sees a pointer to an integer, says that's element 0, and it thinks it's going to have 38 elements, including that one. And this will go into an integer star perfectly well. So that's one way to break up arrays. It gets tricky if you're trying to return something that's a piece of an array. You can get tangled up. But with a Quicksort, we're just moving things around inside the array, right? So there's no harm in passing it a piece. You could also pass it an offset into the array if you wanted, but that's the same thing.
It's not quite that simple. It's not. It's almost. It's kind of rare that your number will actually end up doing them.
Yeah,
Nice.
I worked to make that happen. But it should end up roughly in the middle, right? The cross averages, number of things that are out of place should be kind of the same on both sides. But averages are weird that way. Right, if you flip a coin 1,000,000 times, what's the chance that you get 500,000 heads and 500,000 tails? It's really, really small. Even though that's the expected outcome, right? That's almost never going to happen. All right, if you don't mind being brutal to your compiler, you can probably do something like this also. Do some straight pointer arithmetic. I don't know if it'll complain at you or not. If you declare it to be a data bracket 100, I think it'll give you some talk back. But if it's an integer star, oh really, even with a bracket?
Both of those work just fine.
Yeah, okay, cool. I've only done that with an integer star data. This has always creeped me out a little bit personally, because if you declare this to be a character and you say data plus 37, it adds 37 to the address of data. If you declare it to be an integer, it adds 37 times 4 to the address of data. Right? It does the right thing based on the type of stuff that it's pointing to. but that's different from like an assembly language version of offsetting an address. So that's fine as long as you keep it in mind. All right, so Quicksort's not too bad. It's probably another one I'll give you in 223 to code up. All right, SLP presentations at 3 o'clock. So, and the same drill as last time, okay? So this room will be open. Come in here and grab a table. If you feel like you really need to sit, go ahead and grab chairs, but if not, just take a table and stand. That works well too. I'll be here by roughly 2:30ish. I'll have posters. I'll have a sign-in sheet, and you really want to be sure to sign in. Okay, so you get credit for attending. I'll have that next to the posters. And there'll be the yellow extra credit slips. Okay, so a few comments on the extra credit slips, right? I posted this on Canvas this morning. These are really extra credit, okay? Don't make this the whole goal of the SLP is to get your signatures, okay? I did 1 point per signature 1 quarter. And man, you should have seen people running around getting signatures. It was like, that was all that people were doing. And it was hard because nobody was at their station. They were all running around getting signatures. So that was not a good plan. But it's an extra thing, right? Your goal is to really sit down and have people come over and talk to them about your project, get their ideas, do some brainstorming, things like that. And then as things start to calm down, as more people have seen your stuff, go around and start looking at other people's projects, get some ideas, what they're doing, see what's interesting to you, and so on. Carry the yellow slip around with you and get some signatures while you're doing that. Okay, but try not to get too fixated on the goal. It's not that many points. Okay, it's really just kind of a bonus thing to help you see that. The other thing is, I'd like you to avoid the following situation. Somebody comes to your table to look at your project, and you talk to them about it, and they say, thanks, can you sign my sheet? And you take their sheet and sign it. And then you say, what are you working on? Oh, I'm doing a robotics project. Oh, cool, can you sign my sheet? Right? Try not to do that, okay? Because by the end of last time, that's what everybody was doing, was they were getting kind of like an implicit signature by somebody visiting them, right? If you sign someone's sheet, it should be because they've come to your table and you've talked to them or you've talked to a group that they're in and so on. And Izad students, I don't know if they've got the same heads up or not. So they may come to your table and right, you may talk to them and they may say, what are you doing? Can you sign your sheet? And that's up to you. I'm not going to ask you to enforce. But for you, make sure that when someone signs your sheet, it's because you've actually visited their table. Okay. So I'll be out front roughly 2:30ish. Show up whenever you like, and we'll have fun with this. All right. I will see you then.
Does the webcam still glitch if you just open it right there?
If you open it, what?
Right into that.
I don't have I have my webcam covered up, and I'm using cheese to open this.